Before I go any further, I need to correct the premise of that headline, because there's no confirmed report of James Webb and the Vera Rubin Observatory jointly confirming some specific object together, 3 minutes ago or otherwise. What's actually true and what's genuinely worth understanding properly is something different and, in the long run, considerably more significant. Two of the most powerful telescopes ever built have been specifically designed to work as a team, one built to scan the entire sky, constantly looking for anything that moves or changes, the other built to zoom in and read the exact chemistry of whatever that first telescope finds. And we already have a real concrete example of exactly how that partnership plays out, because it already happened once, with the strangest visitor to pass through our solar system in years. This is the real story of how Vera Rubin and James Webb are built to catch things nobody else can, why Rubin is specifically expected to change how often we find objects like this going forward, and what actually happened the one time this exact process has already played out. If you want accurate space reporting instead of manufactured urgency, subscribe now, because this story is genuinely just getting started. Let's start with why these two telescopes need each other in the first place, because they aren't simply two different instruments doing the same basic job. The Vera C Rubin Observatory, sitting on a mountain in Chile, was specifically engineered to do something most major telescopes were never designed to do: move fast and photograph enormous stretches of sky repeatedly, covering the entire visible southern sky roughly every few nights, for a full 10 years straight, as part of a mission called the Legacy Survey of Space and Time. That design makes it extraordinarily good at spotting anything that moves or changes brightness, a newly discovered asteroid, an exploding star, or critically, an object entering our solar system from somewhere else entirely. According to Scientific American's coverage of the observatory, Rubin is expected to generate as many as 10 million alerts a night, flagging exactly this kind of change, collecting more astronomical data in its first year of operation than every other telescope on Earth combined. It helps to understand just how much raw capability actually sits behind Rubin's side of this partnership, because the numbers involved are genuinely difficult to compare to anything that came before it. Rubin's camera, the largest digital camera ever built for astronomy, feeds data through a processing pipeline capable of generating roughly 20 terabytes of raw data every single night. It operates, according to Scientific American's reporting on the observatory, a volume described as 350 times more data than the James Webb Space Telescope itself collects in an average day. That data gets automatically compared against previous images of the same patch of sky within about a minute of being captured, specifically so that alerts about anything new or changed, an unexpected moving object included, can reach astronomers around the world while whatever triggered that alert is still actively observable. That kind of near real-time processing is precisely what makes Rubin capable of flagging a new interstellar object early enough in its approach for other telescopes to actually plan a detailed follow-up campaign, rather than only confirming after the fact that something interesting had already come and gone. The James Webb Space Telescope does something almost entirely different. Rather than scanning wide swaths of sky, Webb specializes in extremely detailed, sharp observations of individual objects, using its infrared instruments to break apart the faint light coming from a specific target into its component wavelengths, revealing the precise chemical fingerprint of whatever it's looking at. Webb can tell researchers what molecules are present in an atmosphere, how warm different layers of a distant object actually are, and how that composition changes over time, all from a target that might be so faint and so far away that Rubin's wide-field survey would only ever register it as a single, unremarkable point of light worth flagging for someone else to look at more closely. If a story built on real, verified reporting instead of manufactured urgency is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Here's where this partnership becomes genuinely exciting rather than simply theoretical, because we already have a real example of exactly this two-step process playing out, even though Rubin itself wasn't the telescope that made the initial catch this specific time. On July 1st, 2025, an object was detected entering our solar system on a trajectory that immediately marked it as something extraordinary. Only the third confirmed interstellar object ever detected passing through our solar system, following Oumuamua in 2017 and Borisov in 2019. It was given the designation 3I Atlas, and it quickly became one of the most intensively studied objects to ever pass through our cosmic neighborhood, precisely because astronomers now have instruments capable of actually characterizing something like this in real time, rather than simply confirming that it exists before it disappears again. Once ground-based survey telescopes confirmed 3I Atlas was genuinely interstellar, James Webb turned its full attention toward it, and the results were remarkable. Webb's near-infrared spectrograph found the comet's gas composition to be unusually dominated by carbon dioxide relative to water, a ratio almost inverted compared to typical comets native to our own solar system. Follow-up observations using Webb's mid-infrared instrument after the comet's closest pass by the Sun detected something even more significant: methane gas. The first time methane had ever been directly confirmed on any interstellar object in history. A separate isotope analysis published in Nature in June of this year suggested the comet itself could be somewhere between 10 and 12 billion years old, potentially making it older than our own Sun by a considerable margin. None of that detailed chemical story would have been possible without a telescope specifically built to read light apart into its component wavelengths, exactly the role Webb is built to play when something like 3I Atlas gets flagged in the first place. If you found this connection as interesting as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's worth directly addressing why an object like 3I Atlas ended up attracting the kind of terrifying framing implied by headlines like the one leading this video, because the object did generate real public speculation about whether it might be something other than a natural comet. Every measurement gathered on 3I's Atlas, its rotation, its coma behavior, its gas production rising and falling in direct response to its changing distance from the Sun, and its otherwise completely ordinary cometary chemistry, remained fully consistent with a natural, if genuinely unusual, comet. A dedicated search by the Breakthrough Listen project, specifically for artificial radio signals coming from the object, found no evidence of anything technological whatsoever. NASA officials described the object at a press conference in November of 2025 as behaving like what they directly called a regular comet. The genuinely remarkable part of that story was never that it might be artificial. It was that real, natural cometary material, potentially older than our own Sun, happened to pass close enough for Webb's instruments to study it directly. Exactly the kind of opportunity a faster, earlier detection from a telescope like Rubin is specifically expected to provide more often going forward. Now here's why Rubin specifically changes the equation going forward. Because 3I Atlas was actually found before Rubin's full survey had even begun, discovered instead by a separate ground-based survey network called the Asteroid Terrestrial Impact Last Alert System. Rubin officially began its full 10-year science survey on June 30th of this year, and according to Space. Comms coverage of the observatory's capabilities, scientists specifically expect Rubin to dramatically increase how often objects like 3I Atlas get discovered going forward, potentially finding dozens of new interstellar visitors over the course of its full mission compared to the mere 3 confirmed so far across the entire history of astronomy. That's not a small, incremental improvement. It represents a fundamental shift from an extremely rare event, spotted once every several years by whichever survey network happens to catch lucky detection, to something Rubin's continuous, systematic coverage of the entire visible sky is specifically expected to catch as a matter of routine, often earlier in an object's approach than previous survey methods have managed. That shift matters enormously for exactly the kind of detailed follow-up Webb specializes in, because the earlier an interstellar object gets caught in its approach, the more time researchers have to schedule detailed spectroscopic observations before the object either becomes too faint to study or passes out of range entirely. With previous interstellar objects, including 3I Atlas itself, astronomers were often working against a tight, unforgiving clock, racing to gather as much data as possible during a limited observing window that would eventually close for good. A telescope like Rubin, capable of flagging a new interstellar visitor considerably earlier in its approach, thanks to its constant systematic coverage of the entire sky, gives Webb and other detailed observation instruments considerably more lead time to plan and execute exactly the kind of thorough chemical characterization that turned 3I Atlas into such a scientifically valuable target in the first place. There's a practical planetary defense dimension to this partnership worth understanding too, separate from the pure scientific interest in studying interstellar visitors. Every new object Rubin identifies, whether it turns out to be a mundane asteroid native to our own solar system or something genuinely interstellar, gets checked against known orbital paths to confirm it poses no risk to Earth. The overwhelming majority of objects discovered this way turn out to be harmless, but the entire practice of planetary defense depends on actually finding and tracking objects in the first place, since something nobody has ever detected can't be modeled or prepared for at all. An interstellar object moving on a hyperbolic trajectory, passing through our solar system only once before leaving forever, generally poses considerably less practical risk than a native asteroid on a repeating orbit that might eventually intersect Earth's own path. But the same detection infrastructure responsible for catching something like 3I Atlas early is fundamentally the same infrastructure responsible for catching anything else moving through our solar system that might actually matter for planetary safety, native or interstellar alike. It's worth being direct about why this specific division of labor works so well, rather than either telescope simply trying to do the other's job. Rubin's wide-field camera and rapid survey cadence make it extraordinarily good at answering the question of where and when something new appears in the sky, but its images alone can't tell researchers what a newly discovered object is actually made of. Webb's instruments can answer exactly that chemistry question in extraordinary detail, but pointing Webb's extremely limited, heavily oversubscribed observing time at the right target in the first place requires something else to have already flagged that target as worth the investment. Neither telescope replaces the other. They're built to hand off a single continuous investigation from one instrument to the next, wide field detection followed by focused, detailed characterization. Exactly the sequence that turned a faint moving dot first spotted by a Chilean survey telescope in July of 2025 into one of the most chemically well-documented interstellar visitors humanity has ever studied. It's worth understanding why humanity only started catching these interstellar visitors at all in the last decade, because objects like 3I Atlas certainly aren't a new phenomenon in the universe's history, only a newly detectable one. Astronomers have long theorized that interstellar objects should be passing through our solar system periodically, ejected from other star systems by gravitational interactions with planets or passing stars over the billions of years since those systems first formed. And what changed wasn't the underlying physics or the frequency of these objects actually existing. What changed was the sensitivity and systematic coverage of the survey telescopes capable of actually noticing something moving on a trajectory steep and fast enough to mark it as genuinely interstellar, rather than simply another native comet or asteroid. Oumuamua's discovery in 2017 represented the first time survey technology had become good enough to catch one of these objects at all, and the roughly 2-year gap before Borisov's discovery in 2019, followed by a 6-year gap before 3I Atlas in 2025, still reflected genuinely limited survey coverage compared to what's now coming online. Rubin's specific combination of a wide field of view, rapid repeat coverage of the entire sky, and automated near real-time detection software represents the most significant single jump in that underlying detection capability since Oumuamua was first found, which is exactly why astronomers expect the pace of these discoveries to accelerate so dramatically going forward. There's also a broader scientific goal both telescopes contribute to, separate from interstellar objects specifically, worth understanding here. Rubin's own observing mission is heavily focused on studying dark matter and dark energy, tracking how the light of distant galaxies gets subtly distorted by invisible matter along the way, work that requires exactly the kind of enormous, consistent, repeated coverage of the sky Rubin was specifically built to provide. Webb, meanwhile, continues pushing observations of individual objects, distant galaxies, exoplanet atmospheres, and objects within our own solar system, to a level of detail no previous telescope could achieve. The interstellar object story is simply one especially clear, easy-to-follow example of a much broader pattern. Rubin's systematic wide-field surveys repeatedly flagging targets that other, more specialized instruments like Webb then follow up on in far greater depth, a collaborative structure astronomers have specifically designed modern observational astronomy around, rather than expecting any single telescope to do everything on its own. So what does all of this actually add up to? There's no confirmed report of James Webb and Vera Rubin jointly announcing some specific terrifying object together, and treating this as breaking news would be inaccurate. What's genuinely true, and worth paying attention to, is that these two telescopes represent a deliberate complementary partnership, one built to scan the entire sky constantly for anything new or unusual, the other built to study whatever gets found in extraordinary chemical detail. We've already watched that partnership produce real results once, when 3I Atlas was discovered and then extensively characterized by Webb, revealing unprecedented methane detection and hints of an object potentially older than our own sun. There's a reason this specific kind of story tends to get exaggerated into something more dramatic than the reality, and it's worth naming directly before wrapping up. Real, ongoing scientific infrastructure, two telescopes handing off discoveries to each other, incrementally improving humanity's ability to catch and study rare cosmic visitors, doesn't produce a single dramatic headline moment the way a fictional, confirmed, terrifying object would. It produces something slower, and if you actually sit with it, considerably more impressive, a genuine functioning system built specifically to make sure the next 3I Atlas doesn't slip past us the way so many similar objects almost certainly did throughout all of human history before now. If stories like this, the accurate version rather than manufactured urgency, are what you come here for, subscribe to this channel and turn on notifications, because Rubin's survey has barely started, and there's a very real chance the next genuinely strange visitor to our solar system gets caught considerably earlier than 3I Atlas ever was. Thanks for watching, and I'll see you in the next one.